Let's focus on some math. And some of you, it's a welcome chance to focus on something maybe than other things that you've been focusing on recently. So here we go. We were on Friday starting to graph by hand. And I was saying that I want you guys to be able to graph all of these by hand. And then you were supposed to go home and check them out and try them. I'm not going to ask because I don't really want to be disappointed. So instead, for what I'm going to do right now is go through and graph them very, very quickly. And if you guys need to follow it more carefully later, you may. What I did on Friday is I started making tables, yeah? However, how many points did I choose so far for number 12?
3.
I only chose 3. Why am I choosing pi over 6s? Sines 1/2. Yeah, I don't want to choose pi over 3s or root 3 over 2. That's a decimal. I don't want to choose pi over 4. If I don't have to, sometimes there's no way around it. But if I don't have to, I'm not going to. So instead I'm going to choose the pi over 6s and the 0s and the 90s. So then at the pi over 6s, we can see that, first of all, hold on, at 0 we were out 2, which is why I have my little dash mark at 2. Remember, this is helping us avoid drawing a huge old polar graph that we would pretty much massacre anyway. Come on, let's be honest. But we don't need that snazzy big old polar graph. So as we go to graph, I know 0, 2. Kelly, Yuki, shush. As we go up to 2, that's just on 0. What can I also say about pi? It's not 0. Careful. At pi, sine is?
0.
Oh, it is 0. Yeah, there you go. So it's going to be 2. Sorry, I thought we were saying 0. We were talking about when it equals 2. So sine is 0 at both 0 and pi, so I can put both of those. At pi over 6, I can say that, well, hold on. At 1 pi over 6, sine is 1/2. That's 1. I have that. Where else can I say that sine is 1? On the opposite side, because isn't sine also positive in this quadrant? Okay, so I can put 1 there also. What am I going to do down here, though, at 7 pi over 6 and 11 pi over 6? Because 5 pi over 6 is also a positive 1, because it's a positive 1/2. No, sine in the second quadrant is positive. Oh, sorry, Katrina was asking about this one, right?
Yeah, I thought you said it would be on the opposite side. Right?
Well, we're just now talking about quadrants 3 and 4. So let's think about those. Quadrants 3 and 4, sine is equal to what? Not positive 1/2, sine is equal to negative 1/2. So at 7 pi over 6 and 11 pi over 6, negative 1/2 times 2 is negative, but minus a negative is positive. Isn't that going to be 3? Oh. So I need to go more than just 2, right? I need to go 3 and 3 and 3. I really don't need 3 up there. And I'm going to go ahead and go out 3. And go out 3. Remember, we're like thinking about the radius. And that's where we're connecting. As though we had the whole polar graph drawn. Okay. So far, wait. What was going on at pi over 2? 0, right? Okay. So far I've gone here, and then here. What am I missing? 3 pi over 2. What's going on at 3 pi over 2? Negative 1. Negative 1 times negative 2 is 2, and 2 plus 2 is 4. So then this one needs to go down even further. It's a limaçon. Why doesn't the limaçon, technically it's a cardioid. My board's been really rough. I've already oriented it like 3 times today. Why doesn't my limaçon have an inner loop? Yeah, because this radius will never go negative. This radius will never go negative. Now, I'm trying again. Maybe it'll stick this time. Okay. Number 13. As soon as you see it, what should you guys be thinking? It looks like a limaçon.
There can be an inner.
Can be negative?
Oh,
Why is that helpful?
Because code -1
So I'm probably going to have an inner loop.
it has has symmetry on the
What kind of symmetry?
x-axis?
Good. It's going to have polar axis symmetry because sine had this kind of symmetry. What was here, we kind of expected to mimic, right? So cosine, what's above, we're going to expect to be below. We're going to expect it to copy this way, not this way like the sine one. What angles do you think I'll be using for cosine? I mean, 0 sounds good, but what else? Pi over 3. Does that make sense? Because that one's going to be a little bit easier. So then when we go ahead and make this curve, what happens if we plug in 0? Cosine is 1, so then 1 plus 2 is 3. Pi over 3 would be a half. That'd be 2, right? And then pi over 2 cosine is 0, but I think more is going to happen, yeah? What's the biggest, though, that this limacon will go? Just 3, because the highest cosine can be, this is the maximum. I didn't find the maximum over here yet because when sine's -1, the negative times the negative, this could have gotten all the way to 4, and it did down here. This one, cosine reached its maximum potential right away. Or its maximum radius, I should say. So it's going to hit 0 right there. My pi over 3s, I'm going to go ahead and sketch them. I'm going to check my pi over 3s as I go around. This pi over 3 was 2. Remember, turn that to radius as though it was a circle. And that's going to be right there. Then I have 1. Okay, what's going on at 2 pi over 3? -1/2. So it's going to hit 0. What's going to happen at pi? -1. 1 minus 2. Okay. Can you guys follow the motion? This is the 0 from the 2 pi over 3. From 1 pi over 2. So at pi over 2, up 1. And then 2 pi over 3, 0. And then pi is -1. Okay. No. Pi, remember, pi, instead of going towards pi, go away from pi. Does that make sense? Are we okay with this one?
Yep.
This is pi -1, so instead of going towards pi, negative radius goes back. Follow the curve. Do you see it? It curved in on itself. Because polar curves are always curving, always turning. So as we go from 3 to 2 to 1 to 0, it's a big old curve. And you guys already knew it was kind of a limacon, so right here it doubles in on itself. There's the inner loop, and then it comes back out around. Could we check at 4 pi over 3, and at 3 pi over 2, and at 5 pi over 3? We could. What would it show? A limacon with an inner loop. Yeah? Okay. What's going to change on number 14? The maximum will be a little bit different because we're not doing the same adding or subtracting. Some of you guys are already like, it's a rose with how many petals? 4. Ooh, careful. Since it's cosine, wait a minute. 0 is fine. Why am I going to use pi over 6 instead of pi over 3 and pi over 4? It's a double angle. Yeah, so I like the pi over 3 eventually, but for this one, it's going to happen at different places. So when I go to draw my graphs, I'm going to have my pi over 6s. I have my pi over 4s. And I obviously have my 0, pi over 2s, and all that sort of thing. So when I plug in 0, what's going on? Cosine of 0 is 1. Okay. So it's going to go all the way up to 4, right? Okay, you guys are already plugging in at pi over 6, which is going to be pi over 3. 1/2 times 4 is 2. So pi over 6, I can go out to my 2. At pi over 4, pi over 2 is what happens when I plug it in, which will be 0. So now I'm in here. Now, hold on. Where should I go next? Pi over 2?
Pi over 2.
Yeah, pi over 2.
Pi over 3?
Yeah, pi over 3 works.
Why would pi over 3 work?
2 pi over 3.
Because it'd be 2 pi over 3, which will be negative 1/2. What's negative 1/2 times 4?
Negative 2.
Negative 2. And then pi over 2, that'd be pi. Cosine of pi is negative 1. Okay. So I'm going to keep going because these ones also have nice values. So pi over 3. Instead of going 2 towards pi over 3, we're going to go 2 away from pi over 3. So here's my 2 right here. Intersects. Then negative 4 is going to be down here. You guys follow the pattern?
Oh, they draw it like that. Yeah. And it's to the...
Whoa, I thought it was a 4-petal rose. If you were to keep going, 2 pi over 3. 2 pi over 3 would be 4 pi over 3, which is also a negative 1/2. Sorry, yeah, it'd be a negative 1/2 times 4. So instead of going towards 2 pi over 3, I'm going away. I'm going to come right back here. And then if I go to pi over 4, once again, that's going to be 0. So I'm coming back here. So as I curve in. Then as I go to 5 pi over... Oh, I didn't do my pi over 3s over here. It's a little bit off, but it's close. As I go to 5 pi over 6, that's going to end up being 5 pi over 3, which will be positive 1/2 times 4. And positive 1/2 times 4 will be 2 right out here. And so if you notice, it's actually going to end up eventually making your 4-petal rose. But it takes you a little while to figure out the spirals and be like, oh, I see it. Okay. Just had to finish it. Katrina, you had a question. Hi, kid.
That on the bottom,
Yeah.
in the 4th quadrant, there's a dot on pi over 4. Is that supposed to be there, or is it supposed to be on the pi over 3?
I had to kind of redraw my line. So I think this one ended up being my pi over 4 line.
Yeah, so is that dot supposed to be on the pi
So
over
this one
4, or is it supposed to be on the...
should have been on the pi over 3 one.
Okay, sorry, I was...
No, that's okay. I didn't realize that I hadn't drawn my pi over 3 lines. Okay. We didn't even get to number 15. We did 12, 13, and 14. But do you guys see how I'm making these graphs?
You have to square root.
Would you have to square root, or could you just plug in?
That looks so good. That looks really satisfying.
You could technically plug in, right? Because theta is in r's. But you're solving for r by plus or minus square rooting, right? Now, guys, once again, is there a page of lots of graphs that if you wanted to, you could go through and kind of memorize?
Yes.
I mean, even the r squared ones? Yeah, and at least have an idea of what's going on. Is it helpful to at least have an idea of it's a limaçon on something? Whether it has a cardioid or like a little dimple, or whether flat or inner loop, no inner loop. It's a good idea to know that it's kind of a limaçon. It's a good idea to know it's a rose, and not just a rose, but that the even one's double. Like, good ideas. Do you have to memorize everything? I don't think so. But you guys know yourselves better. It's up to you. Kyle. Yep. But not for points. It'd be a part of a problem. Here we go. Areas of polar curves. This is where we're going to camp out today and tomorrow. And where I've been saying polar area is going to be our last difficult topic. It's our last topic. But it's our last of the 3 main tricky topics of Lagrange, power series, and polar area. You guys know that for area under the curve, we have to think of representative rectangles, bases times heights, where the bases can be basically found whether it's horizontal or vertical with a dx or a dy, and the heights, whether top, bottom, or right, left, can be found from the function. And we start getting subtractions, etc., when we start dealing with areas between. We start applying the idea of infinitesimally thin and accumulating to volume by putting in actual area formulas with a thickness or a depth of dx or dy. This is still area, it's not volume, so we're not using the differential to make the third dimension, but we are going to use the differential similar to how we did it with rectangles, except when doing polar area, we cannot use rectangles. Everything is originating from the pole, aka the origin, going out to a radius and sweeping over an arc in a sense. So instead, Yuki, make sure you have it. Instead, when we think about accumulating areas, we're not going to be accumulating rectangles, we're going to be accumulating circular sectors. But they're not going to be perfect circular sectors because perfect circular sectors are parts of circles. And if I was to come over here and look at the polar area for just a second, is that a circle? No. Is that a circle? No. Is this a circle? No. Are they arched? Is there an arc? Yeah. But are all of these in general circles? No. There might be. There might be a circle here or there. But the majority of them are not circular. So even though it looks like, oh, we can do that perfectly, we can't. The arc will be a little bit off if we're doing it to non-circular objects. So just like with rectangles and how they be a little bit off of the curve, these circular sectors are going to be off as well. So how do we resolve that? Integration. We have the differences in theta, d theta. We have the differences in theta be our differential, d theta, which is nice because we have our polar curves in terms of theta, right? So we don't have to go changing into terms of x or y. That would just be nasty. We're going to have our differential be for theta. And as those thetas become infinitesimally thin, the area formed by the circular sectors will go ahead and converge to the actual area within the polar curve. But we just have to use the area of a circular sector formula. And the area of a circular sector formula is 1/2 r squared theta, where r is the radius, theta is obviously the angle of rotation that's being covered. But for our purposes, r is going to have a function attached to it, right? So then even though that's the Riemann sum definition, the actual integral is going to be a equals 1/2 times the integral from theta 1 to theta 2 of r squared d theta. Some of you are like, this seems so easy. Even though the struggle is that you have to memorize a new formula. Even though there is a struggle to memorizing a new formula, the big struggle is finding the bounds. Because your brains don't necessarily think so well in polar, not near as natural as they do in x's and y's. X's and y's set the two functions equal to each other, no big deal. The points of intersection are my bounds. For polar, can't a function pass a common point time and time and time and time again?
Yes.
So the problem is that one point actually one point?
No.
That one location can be infinitely many points. We have to know exactly which theta to put with which other theta in order to get the exact area they're asking for, which could be the area enclosed in the fourth petal. Now, I don't normally hear that. It's usually more the area enclosed in one petal or in half the petals or in the inner loop or in the entire figure. But it does start to get a little bit confusing because our brains don't think quite as naturally in polar as they do in others. Let me go ahead and show you a quick demo. No. You have to get the bounds that give the inner loop alone. Does that make sense? Yeah. But there are ones where you have to get area between like the outer part of the limacol and the inner part of the limacol, then you have to do some arithmetic within the integral. Okay, so with this one, kiddos. Oh. Can I change it? Oh, there we go. Okay. As you notice, I can think about each of these little increments as circular arcs. Now here's the problem though. If I was actually doing a Riemann sum, this curve would not be smooth. Does that make sense? If I was actually doing a Riemann sum, these arcs would be a little bit off and it would be disjointed like a Riemann sum for rectangular coordinates. But they're just trying to show the idea that the angle has you sweeping through the curve and going from the pole out to the outermost, and with the 1/2 r squared within the integral with d theta, it will accumulate, and the integral will make them infinitesimally thin and will accumulate them well. Now, what if we were to do something like a limacol? And what if they were to ask us for just the area of the inner loop? Okay, just the area of the inner loop. Okay, I can't start yet, right? Until now. Right? You're welcome. Question, what's so special about that inner loop? Okay, what gets accounted for twice? Okay, that area, if I were just to go from beginning to end, like 0 to 2 pi, I would not just have all this area, I would have this double counted like a Venn diagram. That's true. However, what's so special about the beginning and the end of the inner loop? When does it start and when does it stop? What point? 0, 0. So for inner loops, as long as it hasn't been shifted somewhere, for inner loops, couldn't I just set the polar curve equal to 0 and find the 2 zeros? And so if I just did the area between the 2 zeros, just those 2 zeros right there, I would be able to solve for it, right? However, here's the dilemma. What if I was to, and this is for a harder problem that we haven't even introduced yet, but what if I was to ask for the area between the outer and inner? Because if I just want the area between, do I want any of that? But here's the dealio. If you go 0 to 2 pi, you would have to subtract it twice. But if you did the bounds such that you did not include the inner loop, couldn't you just subtract it once? And then, what if you were to have something crazy like, and they were to ask you just for the area of the inner rows? Huh?
This is what life is about.
Right? That's way too much, even though it's really cool. So how could I get into just that inner area of the inner rows? I'm not even into the inner area, right? You can see the formula right here. It's a fractional argument. Instead of a double or a triple, it's a fractional. But I'm not even to the inner part yet. Ooh. Am I to the inner part yet? No. That's just the first. Okay, now it comes in. Struggle. Does it ever get to the inner loop? Yeah? Where? Yeah. So do you realize that a 0 is one of the bounds, but the other bound is just awkwardly out in the middle of nowhere? All right, we need to get a better idea for polar area. So let's start at the beginning. Areas of polar curves. For a polar curve, r of theta. We're not talking about between or anything crazy like that, just to find the area inside. The area between the pole and, we're not going up, we're going out. We're going out from the origin, out from the pole. The area between the pole and r of theta for theta between alpha and beta is 1/2 the integral from alpha to beta of r squared d theta, and then we just plug in f of theta. That's what we already saw on the page before. Accumulating circular sectors made infinitesimally thin by the d theta and the integral, and accumulated. Everything I'm going to show you are hints that you can use based on the example you've been given. Meaning, is it what you do every time? No. As you notice, there are many different polar curves, and they can ask us for many different types of areas. And sometimes the intersection that you want to find is not a true intersection, meaning it's just an apparent one. Especially if you have two polar curves, it starts to get interesting. But here's some things that might be helpful. Before I talk through those, though, what's this Endeavor card? Endeavor number?
32.
If you only have one polar curve, so we're not worrying about two multiple ones. Here's some intersections that might be helpful. Finding the zeros might be helpful. Except you can't find the zeros in polar mode. Aww, there's no zero feature when you go to second trace. But you can find zeros if you put it in function mode. It's just going to look very, 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 very different when it's graphed in function mode. You can find the period by setting the argument equal to, what's the normal argument of a trig function, sine or cosine? 2 pi, right? Go team. Every 2 pi, the full cycle repeats. It's okay. It's just pre-cal. So, set the argument equal to 2 pi. So maybe knowing that it's going to complete one full cycle in pi is going to help you as opposed to completing one full cycle in 2 pi. Using the grapher to graph in function mode will be particularly helpful if you're trying to find zeros. And P.S. it's the only way to find zeros if you're trying to do decimal zeros, like you know the AP loves to give you sometimes. Number 3, using the pole to help, setting equal to 0 if you can do it by hand. Maybe using symmetry like we talked about. Sine is always going to have what kind of symmetry? Pi over 2 symmetry. Whereas cosine is always going to have polar. Doesn't mean that a cosine can't have pi over 2 also, but we're just going to say it has at least polar. Sine of theta has at least pi over 2 symmetry. Depends on the function as to exactly how intricate it will get. Maybe not intricate, as to how symmetric it will get. And then those basic graphs are going to be helpful too in knowing how they move and getting used to graphing them by hand. That's like getting you more familiar with the motion as to where the different pieces come from when they come in to play, like the inner loops, etc. But at the end of the day, I just need you guys to realize there is no one set always define the bounds, do this. It depends on the polar curve. It depends on what they're asking for. It depends on how it's oriented and when different pieces of it start. But symmetry is going to really, really help. For instance, if they wanted us to find the entire area within a rose, couldn't we just find one petal and multiply it by 5 or 4 or 6 or 2 or 3 or whatever it is that you have? Or if they're trying to have you to find let me think of a good example. The entire area within a limaçon, which is complicated because you guys have already noticed that some of the area is double counted, so we'd have to be careful with that. But it might be helpful Ooh, I closed it down. It might be helpful to use symmetry so that we don't have to deal with how, for most of that limacon, it's headed out, but then for a little bit it's headed in, then it heads out again. It could be helpful to use symmetry to not have to actually go through the entire figure. So anyway, symmetry might not just be helpful for sketching, but might also be helpful for finding polar areas as well. Okay. Okay. Oh, yeah. I'm not sure if I can make the question big enough. Kiddos, write down the function. Let me go ahead and get it dual paged. I'm sorry, it is going to be kind of small, but we'll do what we can. Let me go ahead and go forward a page. Find the area of the region in the plane enclosed by the cardioid. So nothing super crazy, special, weird about this. Just says find the area enclosed by. Just a parenthesis and a period. Why is Kyle like, why don't we just throw it in with 0 to 2 pi and then just square it all? There's no inner loop for a cardioid. It just comes to a cusp. So is anything being double counted? No. Are they asking for only a portion of it? No. How do you get to 0 to 2 pi? That's a full period, right? Okay, go to your calculators, polar mode. I want you to graph it. I want you to make sure your theta min, theta max is 0 to 2 pi in radian mode. And I want you to see, does it only cycle through once or does it cycle through more than once? Degree is not an awful idea to do. Degree is not an awful idea to do. So that if you were to pause at any point, you would be more familiar with the angle that you're seeing. But I think radian is probably what you would naturally be in, hence why I'm like, okay, no big deal. Just make your theta min, theta max 0 to 2 pi. Here's a feature I want you guys to get really used to in polar. I don't want you ever graphing polar with a straight line. I always want you guys graphing with the circle with the tail. Oh, I just passed it. That's a struggle. I want you graphing with the circle with the tail. Why?
You can see the direction.
You can see the direction. But as you see, it's still graphing 0 to 2 pi, still graphing 0 to 2 pi, and look, what's it do? It stops, it completes, it's done, which means, how long does it take to complete one full cycle? Okay, so the math led us right. I was just trying to have you guys think through. It likes rhythm. Anyway, 0 to 2 pi is totally right. But we are going to need the 1/2, and we are going to go ahead and plug in the 2 times 1 plus cosine. All squared, not just the 1 plus cosine part, right? So we would end up with 4 brought on the outside, 2, the integral 0 to 2 pi. Wait a minute, how on earth, if I was supposed to solve this by hand, how am I supposed to solve 1 plus 2 cosine theta plus cosine squared theta?
Split them up.
Split what up? I mean, I can solve for that. That's theta. I can solve for that. That's going to be, right? So I'll have 2 theta plus 4 sine theta, right? But what am I supposed to do for this one when I'm going from... Didn't I have you guys make a point of adding in the power reducing formulas? That's endeavor number 31, I think, right?
Yep.
Okay, what's cosine squared equal?
1/2, 1 plus cosine 2x.
Oh, that's awkward. 1 plus cosine 2 theta. Good. And why does that make the impossible possible? I can integrate this guy, right? So now it would end up with theta plus, don't forget your u sub, yeah? So I'd have sine of 2 theta times 1/2, and I still have my 4 sine of theta, 2 theta, and all of that is from?
Where'd you get the 2 theta plus 4 sine? you said
I integrated, I distributed here and here. I just left them out for that one, and then I integrated.
you separated.
And this is with my power reducing formula.
Oh.
So then I would have 3, because 2 plus 1, right? 3 times 2 pi plus 4 sine of 2 pi plus 1/2 sine of pi f of b minus f of a, which would be 0. 2 and 1 is 3. 3 times 0 is 0. Plus 4 sine of 0 plus 1/2 sine of. Final answer would be 6 pi. You guys got the basic. Introduction to polar area tomorrow. Have your calculators, have your brains, play with the polar as far as you can get. And come with any questions tomorrow. Bye, guys.